Proximal gradient algorithm. Okay, so when we have a constraint set C, we do this projection after the gradient set. Now, what is proximal is that we move this to the F and become an indicator function. We still do it like this, basically project gradient descent. But if I add something here, but it's not indicator, but a general G that's not differentiable, we change the yellow part. By what? You see, this looks like proximal operator with something. Proximal operator is this, okay. This basically is the inf convolution of F and quadratic term. So we have talked about inf convolution previously. And then compared with the projection, this is a projection. These two things both have this part. And here's the thing, this is arcmean. Arcmean means I put an alpha here, doesn't matter because arcmean means I find an x, so I can put an alpha here. But this one is not arcmean on this only, have an f, that's the difference. And what's the difference? Projection basically is just this guy have this special property. If x is in C, 0. If x is not in C, infinity. So that means this thing is a subset of the thing on top. And now this f can be any f, convex. So what's the alpha? Okay, this is what I said. You can actually move the alpha in and out. It doesn't matter because it's arcmean. So now we have projector gradient descent and proximal gradient descent. Projector is doing this other gradient step. Proximal step is doing this. So for this part is indicator function of set C. Then we just do prox of this thing. And prox of this thing is just projection. So that means if f is indicator function, we go back to here. So that means this is the same thing. And now in general is what happens if this is not indicator function, it's something else. Then we have prox of a general convex function. Okay, so this is example. I want to minimize this because L1 norm. So now I do gradient descent on the differentiable part. Okay, then I have this. After that, I prox it. Prox on L1 norm. So what's L1 norm? What's prox? You add your function and then plus a 2 norm. So it will be on x, on x, on x minus a big thing, this thing. Okay, I already pre-minus it, so that's why this is a plus here. So I have this big thing. Then what? This part is L1 norm. So this part is absolute value x1 plus absolute value x2 plus. What's this part? I have a number here. Okay, I have a number here. Okay. And then what? First part minus the first part plus the first part. So I have something here, 1. And then same, something here, 2. I often multiply that as a square. Okay? So this is what? This is, I can just look at everything here. This is the thing on x1. This is everything on x2. So, in other words, this thing is minimized if each of them is minimized. This expression, this is what? Everything only on one component. And I have n of them. So now this, don't forget this is a constant. I called it z yesterday. Okay? So this part is what? This part is absolute value x plus 2. Let's say t is 1. And then what? X minus z. This is given. And then your function is this. And you want to minimize this. Let's say z is 2, okay? Then you have expanded. This is a quadratic. This is an absolute value. So you add them up. So you will have something that looks like this. Okay? You can find this thing. How? You split cases. If this is larger than 0, you have an expression. If this is smaller than 0, you have another expression. Then you have 2 cases. And then you combine cases. So that's the idea. So once you do this, what you get? You get this expression. So what is the closed form solution of this thing? You actually have a closed form solution. It's called a soft threshold. Exactly what I said yesterday. So if I have input, this whole thing input I call u. So originally I have a y equal u. So this is u. Now I have a number called alpha. Alpha actually exactly is this t later. But so the idea is I have a number called alpha. So I also have a negative version. So what's that? Everything on u, if this is after alpha, I go down alpha this much. I go down alpha. Everything before negative alpha, I go up alpha that much. So let me like this. So it will be this, okay? What about the thing in the middle? U0, okay? This thing is a split expression. Let me give you a statistic expression. This thing, okay, that means the solution. This is a solution. It's called soft thresholding. Let me give you another name. So soft thresholding of U actually is what? Now this is the funny part. What is this line? Let me complete it. This line is U minus alpha. So I have a U minus alpha. What is this line? I complete it. This line is U plus alpha, okay? And I have a third line. I have a 0 here. I write this. Actually, the solution is median. This line is the median of these three things. Think about it. In this part, okay, in this part, what you have? You have this thing yellow, and this thing go to the sky. This three line, who is in the middle? This part. Yeah. And then this part, you have this one, and this one, and this one, who is in the middle? This one. Same for the last one. So, therefore, what's the arc mean of something at L1 norm? Is median. And median is robust mean. So that's why this is statistic. And actually, this thing, you may wonder who the heck put the L1 norm there, is like proposed by the statistician. I think it's 1990 something in 2000. Maybe it's Efron. from Stanford. I don't know how to spell. It's something called least angle deviation, something like that. And later on, this becomes compressive sensing and very big, very big. So, what's the difference between projection and proximal? It's the same thing. You find step size, do gradient step, project it. Proximal step, you do find step size, do gradient step, but instead of project it, you do prox it. And prox actually is just general projection. Yeah. So therefore, what's this for? It's now min f plus g. G can be anything. Not possibly non-differentiable. Yes. And you know how to do this prox thing. Easy to compute. Because what's prox? Prox is this. What's this? It's an optimization problem. If your G here, let's say is a PDE here, okay, then no, sorry, this is too expensive. Okay, so G is simple. What is simple? L1 norm. Okay, L whatever norm, LP norm with some funny P, or what? Nuclear norm, largest singular value. All the thing that is non-differentiable but convex. Okay, there are a lot of examples. Okay, so this is example. And then what we do? Well, we just do this thing. What is this? Gradient step. O point, O gradient, negative O gradient, current step size, this is gradient step. After that, you prox it with what? G. And since you have a step size, you scale the G by the step size amount. And this thing, of course, exists. Here's a funny thing. There are a lot of property about the prox thing. What's prox thing? Just recap. If G is convex, you add a quadratic term. This is always strongly convex. Strongly convex means solution is unique. Convex, not necessarily unique because this is also convex, but you have many solutions. But if you're strongly convex, you always have something below you. So you only have one point in the bottom that's unique. Then it always exists. Okay? And then what? How do we talk about the solution? Now we talk about gradient, subgradient. So suppose now I have this, what is this? Proximal gradient descent. Now I do a funny thing. I have an xx. I have an x minus the prox. The reason is I want to change this term into a big thing. So now I also divide by t, multiply by t. So now I have this whole big thing. And then I call this whole thing, which actually is, I call this g. So it's what? This thing behaves similarly to gradient. Important. Number one, this is not a gradient. This just behaves similarly to a gradient. Because this part looks like this part. Number two, this is also not a subgradient. So this actually is something artificial. Okay? This is just an intermediate thing for analysis. So this is called gradient map. So it's like you try to write proximal gradient update. It's a non-linear thing to something that looks like linear. And then what? You can try to bound something. Yeah, this is the idea. And if this thing is 0, which analog to gradient equals 0, if f is differentiable, then you have minimizer. Why? Because if this is 0, you have this whole thing is 0. Step size is positive, we don't care, so we have this thing 0. This thing is 0 means x equal this. What is this thing? New point equal O point, fixed point. That means we converge. And since we have converged for what? We are doing convex optimization with a strongly convex part. Therefore, it's not a local minimum, it's a global minimum. So we reach global minimum. Okay, so this is called proximal map. So what is setting here? Setting here, f differentiable, that means I have Lipschitz continuous gradient. And then what? Convex, of course. G is what? Convex, but now G can be non-differentiable. And prox is, you know how to do the prox, inexpensive, easy to compute, okay? And you also assume exists solution, okay? Now we have to talk about subgradient because we have something non-differentiable, so that's we call. This is the subgradient, right? This thing is gradient if f is differentiable. But if this thing is not differentiable, I put a G here. Okay, subgradient always exists what? If x is in the relative interior of dome H, okay? Unlike gradient, you can have multiple subgradients. Okay, we talked about yesterday, this is subgradient, this is subgradient, this is subgradient, okay? The set of subgradients is called subdifferential, okay, we have a bunch of subdifferential. Okay, if Q is a subdifferential of H, then you have this inequality. Yeah, that's what we talked about yesterday, right? So now then we have to talk about how do we prove. If we run this, it converges as the same as gradient descent. So we have the classical setup, so let's do it. F is L smooth. L smooth means gradient L Lipschitz cannot be too, know this ring, right? So you have something on top of you. So your F is below a quadratic x. So x, and then this is the quadratic term, L. This L, the L is larger than the Hessian of this point at this point. So this is one. And then what? F is convex. Convex what? Again, this again. So this line below quadratic. I move term. See, this is what? Fx smaller than this one go to the other side. So I have this part. Now I have 1 and 2. They are in the same arrow. So I add them up. This fx and this fx kill each other. This fy stay. This fz stay. So now this is tricky. I have a 3-point expression. yzx. So now put the y into the proximal gradient update. So this is what? This is a new point. So I put this. So I have this whole thing smaller than this whole expression, but all the y change to red. What is big F? Big F is small f plus small g because we are doing this. This everything is on f at g. Now is f. Okay, and the same at g. So is this one at g what? At g on this particular point. So if I add g on this particular point, this whole thing is the big F. And then I add g on a particular point. I have this part. What is this thing? This is actually adding g. I have this whole thing. Okay. Now we need to handle the g part, the non-differentiable thing. So what is subgradient? In this case, I have this thing is this funny thing. So I have this star. This basically is a gradient. I rearrange this line. Why? Look here. This angle is in smaller. I have larger. So I want to make the direction agree. So I have this thing. I move this part to the other side. This part smaller than gz minus this big thing. Now I have this, okay? We have this expression. We want this thing to be smaller than something, and then we can Q it. This is the idea. Then we want this. What is this? You may not know why this is true. Because there's a funny thing here. This is the tricky part. This part is saying that I can cancel the f here. Actually, this is the idea. I have a f and then z minus x tg. This blue part. I want to cancel this part. So that if I put it here, this part will be q with here. This is the idea. So I want somehow get q to look like this. See, this part and this part are the same thing. Okay? So actually I want to get something from these two expressions. So this idea. So now we need the prox and subdifferential. W is the proximal update of a x. If this W is the arcmean of this thing, right? Then W is the optimality point of this problem. That means 0 belongs to the subgradient of this whole thing. This thing is differentiable, so this part becomes gradient. This part becomes this thing. This G is a general non-differentiable G. I keep everything here. Okay? So I have 0 belong to subgradient plus this. This is a set. So this is Minkowski sum. But this is a singleton. So I just write normal plus addition. So now this. Then what? I move this to the other side. Yeah? Then I have this. And since there are T and there are T here, so I don't write down the T in the F. So now I have this thing. So it's saying if W is the next point after proximal gradient step, then I have this funny expression. This thing, what is this? This minus gradient F inside subdifferential of G at the optimality point. Now what? This thing, I move, then this thing is Gx because of this. And then Gx is minus gradient is a subdifferential of this. So that means this thing is a special subgradient of G at the new point. So see, G of A smaller than G of B, no, actually it's larger than, but I have moved the term left and right. So now I get this thing. Yeah, this idea. Let me try to summarize what I did. I start with subgradient because it's not differentiable. Now I need to know what are the AB. I look at here. This is a funny term. Though, so AB, one of them is this thing. That's what I do. And then what? I want to do this. So the arrow is smaller than. This is larger than. So I make it smaller than in the beginning. Then what? Now I need to know what I want for the Q. The reason why I want to do this is because I want to remove this by a bigger box. And the idea of using this bigger box is to Q something here. If I can Q this guy, then I have what? Function, new O point, plus something positive, going down. So I want to create a thing to Q this time. So that's why I want a Q to look like this. So that's why I make this. And what I do here is subgradient, optimality condition. That's it. Okay, then now I have these two lines. This line is this line, first line. The second line is this line. So now I have these two lines. So I add them up. This G thing and this G thing Q each other. Then what's next? I now have this big thing. So this FZ stay, okay, this GZ stay, they together become F. So this two part is FZ, which is good. I have big F, not small f. Okay? So now I have this two, and then now this norm thing stay here. Okay? Now I have to deal with this big thing. This big thing, this bracket and this bracket are the same bracket, so I keep the same bracket. So here I have negative G with this, but this is negative, so I kill this guy. This is what I want, right? So I kill this guy. I live with this G. So now I have this thing. Now this thing. This term is big F. And then I let Z is X star, so I have optimal value. So now this, so this Z is X star. There's no other Z, so now I go to here. Okay? And then what? I take my step side, use a classical step side 1 over L. This classical step side, then what? This term, T is 1 over L, actually not 1 over L, smaller than 1 over L. Then this thing will become, cancel out the T. I have one T, but smaller than. So now I have this thing. Okay? And now what? This G and this G give me G squared. This is G squared. Combine. Okay? I will get a negative because this is negative G squared. This is plus half G squared. So I have minus half G squared. So now I get this. Good. So now I have new value smaller than optimal linear term norm. So I have this thing. Now what's next? This is now the most tricky step. Right? This is what? This is A inner product B minus C. So what is, and this is what? This is norm A. Okay, so I have A, B minus C, norm A. So I'm going to do a three terms thing. I get this is what? B minus A minus B norm squared and then B minus A. no, C minus A. Yeah. So basically it's a ABC thing. So this is just crazy algebra thing. And then what? I now have this thing. The idea is what I have. New value smaller than optimal value, something totally larger than 0. This can be negative and positive, I don't like it. But now with this, now I have new value smaller than optimal value. This, okay, what is this? This thing, good, is new value minus optimal value smaller than difference between two norms. Because this is exactly what x minus tg is the proximal gradient update. So it's a new value. So let's go again. K equals 0. This is the difference between one, and then you have seen this many times. So let me do it again. So now I'm going to sum of them. So all this part, sum to give this thing. This part, if I use the constant step size, all of them is 1 over L, then I take out the 1 over T. Okay, good. All this part, this is a plus, this is a minus. Cancel out. This is a minus, there's a plus here. Cancel out. So again, this part, gone. I'm only left with the first two. The first one and the last one. I don't care about negative, so I remove it. So this thing smaller than this. What is this? Now I have this. And since I have going down, then I can just put this as the last term. So this is any I. Now I remove it to the last term to remove the k. Okay, then what? Then this thing smaller than this. And this is on fixed k. So this summation is a constant. I have k time. I put this below, I have this. So it means convergence rate of proximal gradient descent is the same as gradient descent, even for non-differential function. So that means what? That means you mean f and you mean f, this is differentiable, I call it diable, not, okay, for g. This is f plus g. Then you do gradient descent. What is gradient descent? X equal x minus alpha gradient. What is here? Same. And then you prox it. This is the new part. They behave the same thing. This convergence rate is this. This convergence rate is also this. The additional thing is, because this is not differentiable, so you do everything using this convex analysis. Here is not. You need to do this thing. So you have subgradient, and also you have what? Epigraph. Support, infinity, because you can allow this thing to go to infinity actually. So they behave the same. The new thing is a prox. And now with this in mind, this is called convex optimization, because convex does not mean you need differentiability. This is convex function, but not differentiable, not differentiable, not differentiable. So now you can differentiate any, minimize any convex function, regardless of differentiability. And you just do the prox. What's the prox? You just do this thing. If this thing is doable, then your minimization is doable. And of course, this thing has to be cheap. And then the funny thing is you need to know this G thing. This G is to make the proximal gradient step looks like gradient. So it's an artificial thing. Yeah. It's not subgradient. What is a subgradient? It's the G minus gradient is a subgradient. So it's funny. You do the analysis based on subdifferential subgradient, you get this. So what does it mean? It means for any f, you always decrease with a speed 1 over k. Of course, if your f is very bad, then L is bigger. But still, you decrease 1 over k. An example, how do you derive the prox of one particular problem? This is a popular problem, so that's why I do it. So I want to do this. So now you should know this is the proximal operator, proximal gradient descent. Then my solution, my answer is I want to now tell you how do I get this. This is the idea. Okay. So we have a point after the gradient step, and the prox term is this, right? We have a funny blue thing. This is a gradient step. So this is the prox term. Everything here is differential, is not separable. This is 2 norm square. So I have this. This is 1 norm. So I have this. So this one basically is a big summation sign. And every component is just 1 to 1. That means xi do not touch xj. Good. So I have this. So that means actually I have a scalar function to this. So I have a scalar function to this. So what's the answer? I told you, you don't need to worry too much. You just say, okay, this thing is what? Quadratic. Okay, quadratic square. And then what? X larger than 0, then you have lambda x. X smaller than 0, then minus lambda x. Now you have 2 quadratic functions. You take the dd equals 0, get the solution. Done. But this is the simple idea. But what happens if you do it other way? So this is the idea. So what is this? Exactly is this, right? Okay, you now remember, this is optimality condition. Then what? This thing I told you yesterday, this is not a function. This is not a function because 1x gives you more than 1y. This is strictly speaking, it's not a function. This is called set value analysis. This is the subdifferential calculus way. What's the normal way? Normal way is you split them, then you do classical calculus. What about the subdifferential calculus way? This is a subdifferential calculus way. 0 belongs to this, right? This thing, this f is quadratic plus absolute value. So I have this. This thing is differentiable, so this is gradient. Okay, so I can split them. I have this. This thing I just told you is not a function. This is not a function. But I don't care. I add it. This is called sine function. Okay, then I have this. Then this part, differentiable, I just have this. So 0 belongs to singleton plus z. If my y is here, then I will have singleton plus singleton. Then I have 0 belong to some number. Okay, but if this is exactly at this funny region, then I have a z. So I have this. So basically I have this. Okay, now I move this to the other side, so I have this. So this is the idea. If y belongs to this thing, then x star is a smoother. Then how do you solve it? Now x is id, that means doing nothing, times I, and I assume I can factor them out, like operator thing, and then move it to the other side. Here's a funny thing. What is this thing? This is like a function, this is like identity, so this is something like what? Something like you have a matrix A plus lambda I. You can imagine lambda is here, but it doesn't matter, so I can put lambda here, it doesn't matter. So this thing is always what? Non-singular if the lambda is good. Or in other words, I have a lambda here, but lambda is very small, then this is always non-singular, then I have this. I put it on that side. And since this is non-singular, it's unique. So now I don't have this. If I move to the other side, I have equal. Okay? Then I have this. This thing have a name. This is actually called resolver. This is a linear algebra operator theory or PDE. Yeah, that kind of thing. So basically, the classical thing actually I think is this. Yeah, is this. But it doesn't matter for the sign, because sign can be negative. Okay? So this is the idea. So this thing is the idea, is that what we are doing is that I have this. You now want x star to be something, a function on y, and the function exactly is this thing. Is to do the inverse of this thing. Then how do you get that? Method 1, do the classical calculus. Method 2, this is what? Figure. I have x plus sine x, right? This is sine x. This is x. These two add together give me this. And I have what? Y in this. Now I want to write something as x something y. Well, I just flip this thing along the curve, I get this curve done. And this curve have this funny expression. What is this funny expression? I told you, I have x here. If x is too big, I go down. If x is too small, I go up. And at the same time, this actually is the median of three lines, the first line, the second line, and the third line. So this blue thing actually has this expression, or you write it as a median. And then now, let's go back to here. So if I have this, I can write this update as a T operator. What's T operator? Is this thing on the updated x. So this is updated x, okay? This is updated x, 0 point, gradient, step size, in the ith component. What is this two bracket? This is because of this expression here, the T expression. So this will be what? This is the proximal gradient step. Historically, this is called ISTA. Anyway, it's just proximal gradient descent, okay? And then you can solve it. This is a simple example. So that means what? That means suppose I have an x, I'm going to have 3 non-zero, and I get some b and some a. So that means I have an x, I only have 3 numbers. Okay, 3, 4, 1, and then 0, 0, 0, 0, 0. And then what? And then I have a process A, I get another vector, and I add noise, so I have something. This is my B. Now I give you B. Give me back the A as sparse as possible, because I know X is sparse, and I get it back. So I have 1, 2, 3, 4. What I get is 1, 2, 3, 4. Numerically not perfect, because this one also slightly high. But it's very close. And the error, you see, after 500, almost 0. And I start with a random x. That is rubbish. But I get the solution. Why? Because this problem is strongly convex. If A is full rank, of course, there's only one global minimum. Then, of course, if I solve it, I should get this back. So this is an example of proximal gradient descent in action. And in general, now you mean any f plus g, you can do it.